short summary at the top of the worksheet. Very important, the formula pH we calculate as minus the log of the hydrogen ion concentration, and then I said to you later on when we do equilibrium, I'll explain this further. But for our acid-base reactions, it occurs in a watery medium, and there is an equilibrium between hydrogen and hydroxide ions. It will always give you a value of 10 to the power minus 14. All right? So if you get given the one, you can work out the other one. Or if you get given that one, you can work out that one. No. All right. So the first calculation, calculate the pH of the solution if the hydrogen ion concentration, okay, hydrogen ion, square brackets means concentration, is equal to 1.4 times 10 to the power minus 5. Your calculation, just very simply, pH is minus the log of the hydrogen ion concentration, so it's minus the log of 1.4 times 10 to the power minus 5, and that gives you an answer of 4.85. Okay. Yes. Yes, because then it's not correct. Okay. Any questions there? This was just straightforward. Okay? Then the next one. Determine the hydrogen ion concentration if the pH is 8.5. Now you get given the pH, it's 8.5, and we want to know what is the hydrogen ion concentration. So we have got 8.5 is equal to minus the log of the hydrogen ion concentration. So you need to take the anti-log, I don't know what you call it nowadays, second function log, okay, of 8.5. Waarvoor? Determine, no, it says determine the hydrogen ion concentration if the pH is 8.5.
Yeah, no, hydrogen ion concentration equals 10 to the power.
No. This means that for pure water, that is equal to that, which is 10 to the power 7. Okay? The pH is therefore the hydrogen ion, so for pure water, the pH is going to be the hydrogen ion concentration, which is 7.
Ja, maar soos kyk, ek het hom nou hier so gedoen. Nee, ek daai van en toe werk dit op dieselfde antwoord.
No. Yeah, this is the anti-log. It is right, excuse me. That is right. If you did it physically, yes. If you didn't have a calculator that you push the button. Because when you push the second function log button, it does that. Yeah, people, the hydrogen ion concentration is equal to 10 to the power minus 8.5. Are you with me? If you push the log button, that is what the log means. Yeah. Remember, there's a minus. Look, over here you've got the opposite of log. So it's second function, log of 8.5, but there's a minus. Do you understand? Okay, so it gives you a value then over here of 3.16 times 10 to the power minus 9 moles per decimeter cubed. All right. Joshua? Jy lyk soos die denker. Wat het jy gedoen? Is jou nie reg nie? It is right.
Nee, maar juffrou 3.1 sê, ek 3.5 sê.
Okay, but that's probably just written down wrongly. 3.16. Just check on your calculator if you put in second function anti-log or second function log. Okay, Number 3. Number 3 says, what is the pOH of a solution whose hydrogen ion concentration is 2.75 times 10 to the power minus 4? Now, you can do it in one of two ways. pH is minus the log of the hydrogen ion concentration. So pOH is going to be 14 minus the pH. All right, but they've given us the hydrogen ion concentration, so minus the log of 2.75 times 10 to the power minus 4, that gives you 3.56. But this is the pH. The question asks, what is the pOH? Kari? Okay. So the pOH, now this is technically not really part of your syllabus, but I've put it in because it's got to do with the manipulation if they give you a base without the hydrogen ion concentration that you can get to it. Okay, so it's just, this is like a little bit of extension. Okay, so the pOH is going to be 14 minus 3.56, which would give you 10.44. You could have also gone and said, the other way of doing this calculation, let's do it in a different color. You could have gone and said that at equilibrium, well, or in a system where we have an acid-base reaction, the hydrogen ion concentration times the hydroxide ion concentration must equal 10 to the power 14, minus 14. All right, and then you can go and substitute in the one, and you can work out the hydroxide ion concentration, and then you can go and work out the pOH. Just hang on with your question. Okay, I quickly want to do the calculation. So we can say 10 to the power minus 14 is equal to our hydrogen ion concentration, which is 2.75 times 10 to the power minus 4, times the hydroxide ion concentration. So now, can you see, we can work it out. All right? That divided by that would give me the hydroxide ion concentration. So hydroxide is going to equal 10 to the power minus 14 divided by 2.75 times 10 to the power minus 4. Yeah, well, it comes down to the same thing. It's not exactly the same. It gives you 3.63 times 10 to the power minus 11, okay, with a rounding. And then you can now go and say pOH is equal to minus the log of the hydroxide ion concentration. So it's minus the log of 3.64 times 10 to the power minus 11, and that should give you 10.44. Okay, Janus, wat wil jy vra? You multiply them. Yes, it is absolutely got everything to do with it. It's got to do with the equilibrium between hydrogen and hydroxide ions. Okay, acids are proton donors. The more hydrogen ions you have, the lower the pH. No? Okay. All right, next one. Determine the pH of 0.0001 mole per decimeter cubed sodium. Here we have it, hydroxide solution. Do I have hydrogen ions? No. So there are two ways of doing this thing. All right. One way is to know that in solution, the hydroxide ions times the hydrogen ions equals 10 to the power minus 14. And then you can work out the hydrogen ions, and from there work out the log. In this case, the easiest way for me would to work out the pOH. Because if this is in solution, it's going to break up and form sodium and hydroxide ions. For every 1, I will get 1 and 1. So for every so many moles in the cubic decimeter, I will get the same amount. Do you understand? So I've got the hydroxide ion concentration. So I would simply say is equal to minus the log of the hydroxide ion concentration and that would give me, is it 4? Yes, 4. So the pH is going to be 14 minus 4, which is 10, and it has to be a base. Bases have pHs above 7. Are you following me? Okay? Albert? I'm going to do the other way of doing it. So just try and follow. Instead of working the pOH, I can go and make the statement that the hydrogen ion concentration times the hydroxide ion concentration is 10 to the power minus 14. I've got that one there, so I can get that one. Okay, my equation is going to be, my hydrogen ion concentration is going to equal 10 to the power minus 14 divided my hydroxide ion concentration, which is going to equal, I didn't do it. Quickly work it. 10 to the power minus 4, it's going to be 10. Okay, so what is pH? Minus the log, 10 to the power 10. That's actually minus 10, isn't it? Yes, minus 10. Sorry. 10 to the power minus 10, which is equal to 10. And it doesn't matter which method you use. This manipulation with pOH as such is strictly speaking not syllabus. But it's easier than that. And you have a smaller chance of making an error because you're working with smaller values. It's just, yeah. It comes down to exactly the same thing. But that is why I've shown you that method, because it just is sometimes easier. Okay, then. They say number 5, the pH of a cool drink is determined to be 4. What is the hydroxide ion concentration? Say again? Yeah. Okay, so pH 4 is equal to minus the log of the hydrogen ion concentration. So second function log, the hydrogen ion concentration is going to be 10 to the power 4. You with me? So what's the hydroxide ion concentration? Well, remember, hydroxide ion concentration times the hydrogen ion concentration is always equal to 10 to the power minus 14. Now we've got that one. So the hydroxide ion concentration is going to equal 10 to the power minus 14 divided by 10 to the power minus 4, and that is going to be 10 to the power minus 10 moles per cubic decimeter. All right. You could have also said over here, same thing. But you need to be able to see the picture. If the pH is 4, what would the pOH be? 14 minus 4. And what is the pOH? Well, it's the log of the hydroxide ion concentration. So then you can simply go and say 10 is equal to minus the log of the hydroxide ion concentration, which should be 10 to the power minus 10. You follow? Okay. Yeah, but okay, some people it does confuse. It just depends. All right, then. What is the pOH of a solution whose pH is 3.45? 3.45, that is the pH. So we want to know what is the P... Oh, number 6. Okay, sorry. Number 6. The pH of a solution is 3. What is the hydroxide ion concentration? So I'm going to do it. If that is the pH, then the pOH is equal to 14 minus 3 is equal to 11. So if the pOH is equal to 11, that is minus the log of the hydroxide ion concentration. 6. So then the hydroxide ion concentration is second function log that is equal to 10 to the power minus 11. Are you with me? Albert? Volg jy? Okay. Must I do the other way of doing the calculation? I can quickly do it. Just, all right. If pH is minus 3, then we have 3 is equal to minus the log, the hydrogen ion concentration. So the hydrogen ion concentration is 10 to the power minus 3 moles per cubic decimeter. So now we don't want that, we want the hydroxide ion concentration. So we know hydrogen ion concentration times hydroxide is 10 to the power minus 14. So 10 to the power minus 3 times what is equal to 10 to the power minus 14. So hydroxide ion concentration is equal to 10 to the power minus 11. All right, there we go. Julle is so stil. Number 7. Yeah. What is the pOH of a solution whose pH is 3.45? If the pH equals 3.45, the pOH is equal to 14 minus 3.45, which is equal to 10.55. All right. Number 8. Het jy hom reg? Yes? Let's go back. All right, number 8. What is the pH of a solution whose hydroxide ion concentration is equal to 9.31 times 10 to the power minus 2. All right. Hydrogen ion times hydroxide ion concentration is always equal to 10 to the power minus 14 in watery solutions. So if we are looking for that one, we've got that one. So the hydrogen ion concentration will equal 10 to the power minus 14 divided by 9.31 times 10 to the power minus 2, which is equal to 1.031. No. Yes. Okay. But that is the hydrogen. What was the question? What is the pH? Oh, we want the pH. So we've got the hydroxide ion concentration. Okay. So the pH, that is going to be 14 minus 1.031. 12.97. Any questions there? Okay. Chorus? Okay. And number 9. What is the hydroxide ion concentration of a solution whose pOH is 2.86? Well, if the pOH is 2.86, then the hydroxide ion concentration is second function log, ne? And that would be 1.38 times 10 to the power minus 3 moles per decimeter cubed. Okay. All right, we can stop there.
always been here for you, and our promise to bring you low prices on what you need most will never change. Get 2 kilos Nam milk or Maere assorted, only $34.99 each, and 175 grams Dettol bath soap, just $10.99, only at ShopRite. One stop, one safer shop.
The wait is finally over! The leaders want to run away with it! Those at the bottom will fight to survive! There is so much to expect! It's as good as it gets! And there is no feeling like that feeling! A game of thoughts, a game of thrills!
Oh, it might just bounce kindly! Even better than that!
Live sports is back on GoTV. It doesn't get any better than catching all the action from La Liga, Serie A, the Premier League, and WWE as it happens. Take it all in. Get GoTV and subscribe for the ultimate live sports on SuperSport with GoTV Max. GoTV. Live it, love it.
Seriously. We have to carry on with acids and bases. I've finished with the pH calculations. At this point, I assume you can do them. No. Okay. Those of you who had problems with them, please work through the worksheet. Come and ask. Okay. In your textbooks, more or less there on page 77, is where we stopped last before I gave you the notes on acids, on pH. All right. Now, this next section has just got to do with pH in nature, pH in your body, and pH of the soil. Now, in nature, plants require a specific pH of the soil, and it varies slightly from the type of plant that you want to grow to whatever. One of the problems that we have nowadays is due to a lot of industrial processes and burning of fossil fuels. There are gases released into the air which cause the soil, among other things, to become more acidic. All right, and then this has to be counteracted by adding bases, lime, etc., to the soil. So therefore the paragraph on the pH of the soil, there's not much more that I want to say there. Just take note, it connects up a little bit with environmental chemistry and acid rain. Okay, remember, acid rain is mainly sulfur dioxide that reacts with water vapor in the air, and it forms H2SO3, that is sulfurous acid. Okay. The sulfur dioxide can oxidize further, and it can form sulfur trioxide, which is also water soluble, and that forms sulfuric acid. Okay. Sulfurous. That one is sulfuric acid. Okay. Yes, and the other one is hydrogen sulfite. I-T-E. Top one. All right. People, with the sulfur, H2S, H2SO3, H2SO4. I think I've had this on the board. That is hydrogen sulfide. All right. That is hydrogen sulfite. And that one is hydrogen sulfate. Okay. You must know the distinction between those three. Okay, now, in your textbooks there on page 79, the heading is Oxides and pH. Now, when we did the periodic table, we started off on the left-hand side with the metals, and we said that the oxides of metals are acids or bases? They are? Bases, yes. And as we move across the periodic table from left to right, and we get to the non-metal oxides, we find that non-metal oxides are acidic. Okay? Then we find some of these oxides are neutral. Right at the bottom of page 79, there are some oxides of elements which are neither acidic nor basic. If they dissolve in water, they do not affect the pH. If they don't dissolve in water, we won't bother with them because we work in with watery mediums. Okay, these are called neutral oxides. The most common one is water itself. And then carbon monoxide is neutral. Nitrogen monoxide and dinitrogen monoxide. So carbon monoxide, nitrogen monoxide, and dinitrogen monoxide. They are all neutral oxides. In other words, they don't affect pH. They are neither acidic nor basic. What does it mean on the next page if something is an amphoteric oxide? Because we started with metals and we said they are basic. Metal oxides are bases. Non-metal oxides are acids. Then we had a few of the oxides in general we said that are neutral. Okay? And now we get something known as an amphoteric oxide. Now, if you're an amphibian, you land both in water and on land. So if something is amphoteric, well, it can act like both an acid or a base. Okay? So in your textbooks, amphoteric oxides, you can write in there they react as both acids and bases. All right. And then there is a block at the bottom of the page, 80, higher studies. They say these are symbol equations for the reactions between chlorides and sodium hydroxide. What is an acid? What's the new definition? Proton donor. What is a base? A proton acceptor. Okay. If I have water and the water does that, can you see? Oh, look at my H2O. The water is acting like an acid because it has donated a proton. But water can also do this. What has water now done? It has accepted a proton. So in this case, water is amphoteric. You with me? All right.